carbon. Zinc is going to be one of them. You're going to have 2 hydrogens, an iodine and a zinc. Tack the other iodine on the other end of the zinc because metals like to be complexed by things, right? And then the bonds that get broken are the ones between the iodine and the carbon and the zinc in the carbon. So you do very similar to the carbene, the dichlorocarbene mechanism. You get one side attacks, it gets attacked back, and then we just have one more bond to break right here, and we just take those electrons and put them down on the zinc, so that the zinc gets to have 2 iodines next to it. Because metals really like when they get to be complexed or hang out with things that have a whole lot of electrons. Just sort of like making positive charges. They like to kind of be held by lots of electrons. So, same rules apply as for the other carbenes, carbenoids. And I'm going to let you guys do those problems on your own. Wait, that's chapter 15. That's also chapter 15. Chapter 16. Aldehydes and ketones. Okay. Cool. So, now we're going to talk about carbonyls. There are a lot of parts to this chapter, and I expect it to take us like, I think I planned like 4 days, maybe 4.5 days. Hopefully I planned 4.5 days in the schedule, did I? Including this is half a day? Okay, so we might actually get through this on time. We'll see. But this is a long chapter. But in this chapter, we start on carbonyls with aldehydes and with ketones. But what we're going to learn in this chapter, a lot of it is going to be, we're going to try to learn more thoroughly now so that when we get to the next 4 chapters that are still carbonyls, or 3 chapters that are still carbonyls, carboxylic acids, acid halides, esters, amides, acid anhydrides, and enolates, anions, chapter 17 through 19. They're also carbonyls, so hopefully we'll have a really good idea of how carbonyls work, and we can, apply that knowledge when we get there. So that's why this is a slow chapter, because there's a lot going on. So this is what the carbonyl group looks like. It is a carbon. It's double bonded to an oxygen. Usually we point those straight up. I mean, sometimes just because of how the zigzag forms, they get pointed a different direction, but if I can help it, I point them straight up. But this is flat in the plane, and this is the, I'm so used to presenting in rooms with TVs instead of projectors because they hate us, and these don't work on TVs. So this is the pi bonding orbital. This is the anti-bonding orbital, right, for formaldehyde. Formaldehyde is the simplest aldehyde. Here we go. Formaldehyde and methanal are the same thing. That's the simplest aldehyde. But in order to get to the simplest ketone, we have to add several more, because aldehydes and ketones are the exact same thing. They're just, hey, there's a carbonyl here. Sorry, staying here by the microphone. It's just, hey, there's a carbonyl here, and there's nothing particularly interesting next to the carbonyl. So it's an aldehyde or a ketone. The way we know which is an aldehyde is on one end, and a ketone is in the middle, because if you have a key and there's only one place, like one possible place for the, I don't know, teeth of the key to go, it's a terrible key. But if you've got a really long carbon chain and you could put the carbonyl anywhere on there, the teeth of the key anywhere on there, you have a much better key, right? It can be different things. Ketone is in the middle. It kind of works. So, methanal from aldehyde is our simplest aldehyde, and the way that we name aldehydes is we just change the, let's see, methane, yeah, so the E at the end, we change that to an al. Much like if we have an alcohol, we would say methanol, now we say methanal. Yes, it is confusing to pronounce, or at least requires very careful pronunciation. Ethanal is also an aldehyde and cannot be a ketone because, of course, there's only two carbons. Both carbons are on an end. So like if you put it here, you've got ethanal because you've got your carbonyl on the first carbon. And if you put it over here, you still got ethanal, and you don't have to put a number with an aldehyde because you always, whenever you're naming an aldehyde, you assume wherever the aldehyde is, that's where you're starting your numbering. That's carbon number one. If you need to name, it starts getting weird and you absolutely think you need to name a molecule not by the aldehyde, or at least you can't start numbering one right there, you shouldn't be naming it as an aldehyde. You should be taking, I mean, basically if you can't start the numbering at the aldehyde, then that carbonyl should be on a side chain. But honestly, if you're naming, when you find the longest carbon chain, you want the longest carbon chain that includes your major functional groups. So you can pick the not as long carbon chain that includes your aldehyde, right? And then you don't have to number at least the aldehyde part. For ketones, instead of an al at the end, we put an one, propanone, or acetone. This specific one doesn't have a number because, well, there's 3 carbons, so if it's a ketone, there's one option for it to be at, but any other ketone, you are going to have a number indicating which carbon that's on. Question, did you guys learn, let's do 2, 3, okay, so this is 2-pentanone, or did you guys learn that this is penten-2-one? Which of those looks familiar, up or down? Both? Okay, cool, excellent. Good. I think it's, yeah, I guess that makes sense that this is always taught now. When I took organic chemistry, this one had just, yeah, the MCAT had just started using this, and nowhere else used this, and so we had to learn both because it was, anybody who's taking the MCAT, here's the way you're gonna have to name it, everybody else can do the other way, unless there's too many functional groups, and it was wild and new, at least to my professor, so it seems nice and new to us. Okay, so that's naming. Yeah, select the longest chain of carbon atoms that contains the functional group as the parent alkane, change the suffix to al for aldehydes, and you don't have to number it. If you've got a double bond or a triple bond in there, then instead of anal, butanal, you're going to have propanal, or there's no triple bond here, but you would have YNAL, right, so that you can indicate where the double bonds are. And because these are aldehydes, if there's just one thing that you're putting a number on, even if it's like a double bond or triple bond, something that gets named at the very end. If you want, you can just put the number at the beginning, because the aldehyde, it can't be referring to the aldehyde, right? Like, the only thing that this 2 could be referring to here is the double bond, because aldehydes don't get numbers, ever. They're always 1, no matter what. Oh, okay. For a cyclic molecule, if you've got the CHO coming off of the ring, not if you've got a cyclic molecule, because you can just as easily have this, right? This is not what we're talking about, because this would be cyclohexal, yeah. Ow.
Isn't it ketone or
What?
doesn't that make it a ketone instead of an aldehyde? So it should be
Yes, good call. But this one also doesn't need any numbering yet, because if it's a cyclo, we just, whatever the most prioritized functional group is going to be, you assume that that's a 1. So cyclohexene, you don't have to call that 1 cyclohexene, because there's only one thing in a circle, so you start numbering wherever you want. In this case, they're there. This is the same way. We start numbering wherever we want, which means the correct one is here. Good call. But if we've actually got a ring where we've got an aldehyde coming off of it, I guess that's the only way to make a cyclic aldehyde, then we're going to, instead of al, we're going to have that, we're going to name it carbaldehyde. So cyclopentane carbaldehyde. Just shove that on the end there. In this case, carbaldehyde is our most highly prioritized group, functional group, right? So in either case, we're not numbering the carbaldehyde because we're assuming that's 1. And if we've got something else that we have to number, like up here, we have to say the number for the other thing. But we assume that the most highly prioritized is still a 1. Where's my... Okay. Ketones, change E to an own. Put the number in there to tell me where it is, unless you've got a weird one, like acetophenone or benzophenone, or, okay, that one needs a number, but 1-phenyl, 1-pentanone. So in this case, we're not saying this is part of the, we're not naming this as a benzene, we're saying this has a phenyl substituent group, right? So we're counting 1, 2, 3, 4, 5 carbons. This is, because this guy, this carbon, doesn't have an H on the end, we don't get to call it an aldehyde. Yes, it's on carbon number 1, but the only way we get to call a carbonyl an aldehyde is if on this carbon there's a bond to something, well, a bond to a carbon. So if it's a bond to anything else, then it gets into other types of carbonyls. So 1 bond to a carbon and 1 bond to a hydrogen. That's required for an aldehyde. Otherwise, like this guy, we go into a ketone. So that's a ketone on carbon 1, but like it's 1-phenyl, 1-pentanone because those reasons. We're not going to practice naming aldehydes and ketones because we can do that later. Order of preference of functions. Aldehyde is higher function or higher preference than ketone. So if you have an aldehyde and a ketone, then the same carbon chain, then you can pick the aldehyde to be carbon 1, and you can just do the Al at the end, and you can then do the ketone on there as well. So the ketone that you're going to put on there is going to be a prefix, right? If it's lower priority, it goes in as prefix, unless it's a double or triple bond, because those guys stay at the end anyway. So if you use a prefix, you do oxo. 3-oxopropanoic acid, or if that was just CO8, here we go. Or if this one is just COH. But yeah, 3-oxopropanoic acid if it's not the highest priority oxo, and you number it. Okay, let's get to the interesting stuff. Formaldehyde, formic acid, acetaldehyde, acetic acid. Those are the aldehydes, the common name aldehydes that you're going to want to know. So dicyclohexyl ketone is just going to be a ketone with dicyclohexyl, a cyclohexyl on either side. Diethyl ketone has an ethyl on either side of your ketone. Ethyl isopropyl ketone, one side has an ethyl, one side has an isopropyl. This is not the way you're supposed to be naming ketones, but because chemistry started before we had these nice, very specific, very specific naming system where you can literally go to SciFinder and you can type in the name and it'll give you the structure, or I think it's not always great about doing vice versa. It's not always great about giving you a name from a structure. But if you have a good enough version of ChemDraw, which the university does not provide ChemDraw Prime. If you have ChemDraw Prime, not provided by our university, then you can literally just draw a picture, select it, and then right-click structure to name or name to structure, and it'll go back and forth. This naming existed first, so that's how we deal with that. No, we're not going to do that. Physical properties. Okay, so carbonyls are polar, right? They engage in dipole-dipole interactions in pure liquid. We're not going to have hydrogen bonding just between, like among aldehydes or among ketones, right? Because we don't have the special hydrogen for hydrogen bonding. Even if though we've got this hydrogen is not eligible for hydrogen bonding, right? No, yeah, no hydrogen bonding for that guy. So we are going to have elevated boiling points because these have dipole-dipole interactions in pure liquid. Those are stronger than just the Van der Waals interactions that like hexane is going to have. So higher boiling points, but we're not going to have high enough boiling points that we're going to rival alcohols that have the same number of carbons, right? Because alcohols, they do have the special hydrogen that can hydrogen bond. So those guys, way high boiling points. They're also going to be more soluble in water than nonpolar compounds of comparable molecular weight. But yes, at some point, you're going to get to a point where there are enough carbons that nothing really goes in the water. That's how that is. So, let's see. Okay. These all have not the same number of carbons necessarily, but since carbons and oxygens are of similar molecular weight, if if you take number of carbons plus number of oxygens, you get the same number for each of these, yeah? So we've got similar molecular weights, but instead of actually having to figure out the molecular weight, you just, if it's got the same number of carbons, or if you've got carbons plus oxygens plus, I guess, nitrogens, if there were any in there, those are all similar-ish weights, so make sure there's the same number of non-hydrogen boys, and it'll all be pretty similar. Our highest boiling point is propanoic acid, right? Because a carboxylic acid can hydrogen bond, and in fact, we have such good hydrogen bonding. We'll talk about that later. There's a whole chapter on that. Propanoic acid is really, really good at hydrogen bonding. Carboxylic acids are. Butanol, that's the next highest, because alcohols, they like to do the hydrogen bonding thing. Then we get to butanone and butanal. Honestly, I don't think I could tell you why butanone to butanone has a higher boiling point than butanal. And unless we come up with a really good reason, I will not expect you to know that. Unless we come up with a really good reason at some point. It's like, oh yes, this is an example problem. Here you go, now we know. So, let's see. We can also, these are all aldehydes or ketones, and the solubility in water is going to be a whole lot higher if we've got lower molecular weight, and a whole lot lower if we have higher molecular weight. But it's definitely, this is definitely much more soluble than a similar number of just, let's see, methanol is 1 carbon, 1 oxygen, so the equivalent is ethane, which is gas, but whatever. It's still not going to be very soluble, right, in water. So these are just trends. You don't have to know exact boiling points or anything like this, but you should be able to, if I give you those are, I think, nice, easy multiple choice questions. If I've got I'll choose some of these guys and just put them on there and go, hey, which one's got the highest boiling point? And you are gonna be like, wait, how am I supposed to know that without being able to look that up? Oh, wait. And there should be something specific, like either they're all similar molecular weights and we've got different functional groups, or they all have the same functional group and we've got different molecular weights, different numbers of carbons. So, know those trends. Okay. In 17, we've got time to start this. Okay, reaction themes. One major reaction theme of a carbonyl group is going to be nucleophilic acyl addition. Acyl is, acyl carbon. That guy. So, nucleophilic acyl addition. If we are adding a nucleophile to a carbonyl, then that means that this guy, if we're going to add a nucleophile to that, then we need to find an electrophile on there, right? There must be an electrophile for adding a nucleophile. So we think that's going to be?
The carbon bonded to the oxygen.
Yeah, the only carbon I drew out, right? I'm very good at setting up these questions before I draw them out. Yep. Don't think of them immediately after drawing them out. So, in this case, that guy is our electrophile. We are going to take a nucleophile and add it. So, we've got, you weren't supposed to have any sound. I'm pretty sure no one gave you permission to have any sound. So we're going to call this our nucleophile, and if we add these, switch to blue for mechanism arrows. All right, this guy is going to attack there, that's an arrow, and these are gonna get bumped up here, right? Because carbon does not have energetically accessible d orbitals, so it's not like chlorine where like, if we really want to, and if we have to, then sometimes I guess we can break the octet rule. Not so much with carbon, right? It's up there on the first, well, the first layer, minus the one that doesn't really count with hydrogen and helium. So, our product is going to be, let's do, there's our carbon, we've got that, one of those is our prime, nucleophile, and R. Now we've got this going on. And, yeah, okay. So we call this, do you have that on? Nope, okay. They have this called a tetrahedral, I'm writing all over myself. Tetrahedral carbonyl addition compound. A lot of times, a lot of these reactions are going to have this as an intermediate. Now, if we've gotten to this point, are we done? Well, not entirely, because we've got a charge here, so we probably need to like work it up with acid or water. Honestly, a lot of these can just be worked up with water, but I'm not great at remembering which ones you actually need acid for, but you can work up that with some aqueous acid, and you can make that into an alcohol if you want. And there are other things we'll do with it. So, that is reaction theme of a carbonyl group number 1, nucleophilic acyl addition. No, don't block these. Okay. So these. Okay. Reaction theme 2, resonance stabilized cation. This is a little different. So, this one we're going to start with this, and what we're going to do is we are going to, I'm not going to show this, I'm going to show this the way that I wish I had taught this last year. So, we're going to have that, and we're going to have is what our nucleophile looks like. So, sometimes, basically, we end up with the same thing, right? But this doesn't get to be our first step. And it's not necessarily just because of the hydrogen here. This is going to be, sometimes we're going to have reactions that have to occur in basic environment, and sometimes we're going to have reactions that have to occur in an acidic environment. The best way to figure out the mechanisms of these is not to remember the first step that I'm about to show you. It's to remember, find yourself an electrophile, find yourself a nucleophile, and do your attack. So in this case, this attack would happen and we would get O minus R, and U, H, and that guy has a plus charge. Yeah. This is what would result if we just did that attack, right? And the reaction theme that we're going to see is when we want an attack like this, but we have to be in an acidic environment. Whenever we need an acidic environment, we can only have plus charges. Okay, so basically, figure out what's going to do the attack, do your main attack first, then go back and figure out, hold on, which of these environments does this happen in, and correct yourself if necessary. Because otherwise, there's no really good way to remember. Yeah, that's going over here. We're doing this. Otherwise, there's no really good way to just look at a reaction and go, oh, should I do a nucleophilic attack, or should I protonate this first? Which is what we're about to do. Man, I don't know why they put these science rooms. I bet you anything. The one Revachol Echo 360 room is probably not being taught in for the next 5 weeks. I bet you there are a million Revachol and or Crosley, there are probably a ton of Crosley classrooms that we could be teaching in. And I bet most of those prioritize Blackboard space over projectors, but I guess they hate me, so this is what we get instead. That's fine. I haven't actually worked out since, I was gonna say before COVID, but let's be real, like, honestly before grad school started, so maybe this is good for me, moving these times as a workout-ish. So, this is not our theme 2. This is the work or the thought process beforehand, right? That gets you to, when we do theme 2, we have theme 2, basically, we have to be in an acidic environment. So once we did this attack, we went, oh no, we have a negative charge. Let's go back and fix that. So the way we fix that is we put it in an acidic environment. And we go, hey, how about, oh, we protonate that guy first, because there's no rule against that. Now we have this. So now, and this is going to be a really fast step. This is reversible, but like any those guys are really fast. So we're gonna have that, and then, okay, yeah. And then this guy is resonance stabilized. I'll write it next to it. So remember, this is a reversible reaction. This is resonance. And I know it's really tempting to get them mixed up, so don't. That was helpful, right? So this guy is the way that we can do resonance with that guy. Let's do this. Is we can go like this, and we get I'll sort of try to put those in brackets, right? Resonance stabilized cation. I mean, which of these resonance structures actually, well, and then I guess to go back, you do this. Which of these is going to be contributing more to the overall structure? That one, of course, because, yeah, we've got a positive charge on an oxygen, and you may have heard when we try to put, when we have charges, oxygen likes to have a negative charge, and it doesn't really like to have a positive charge, but, because it's more electronegative, right, than carbon, but once we get to organic chemistry, all of the boys that have a whole lot of electron density and don't like to have positive charges, they all have positive charges at some point, and that's because in order to make anything else have a positive charge, we don't have a complete valence shell. So, yeah, the carbon would prefer to have the positive charge, but everybody would prefer that that everybody has a full valence shell, and so this guy just gets stuck with the positive charge for the most part. So, this resonance stabilized cation, we're going to just redraw this guy. Okay. We're going to take that, and we're going to do our nucleophilic attack. So, now when we do our nucleophilic attack, over there, whatever, we get, oh, and identify our electrophile. I guess it's spelled NU, so it's obviously our nucleophile, but we can color code it. Then we have this. Yeah? We started with a positive charge on this oxygen, so when we attacked and we took another, we bumped one of those lone pairs onto the oxygen, we just got rid of the positive charge rather than making it a negative charge. So now we've got this thing going on. So this attack step is going to be slow, right? And then, yeah, and then we usually finish this out with okay, that's H2O, water, but I draw it like this because it's really nice to have a bond to draw your arrows from, right? Because if we start trying to draw our electron-pushing arrows straight from hydrogen, then that just gets weird because our arrows should come from a source of electrons. Hydrogen does not have any lone pairs. You can't just take it from the actual H, so we can take it from there. So, we have this guy, and we're just going to go, hey, how about we do this, and we end up with a nucleophilic addition reaction. But resonance stabilized cation. And then I guess we would have H3O plus, which makes the acid here, if we start with it and end with it, then the acid is catalytic, right? Okay. Yes.
So when you drew that water right there, grabbing that hydrogen from
Yes.
the nucleophile, the attack comes from that bond right there. It doesn't come from the lone pairs on the oxygen.
A mostly properly caffeinated instructor. Good call. When we're protonating something, yeah, up here is why I drew it funny. H3O plus, I do H dash OH2. Or if we're doing this in a basic environment and we still need to do proton transfers, I'll do H dash OH. But that's because in a basic environment, you're allowed to make hydroxyls, OH minuses, because you're allowed to have negative charges. In an acidic environment, which is sort of this guy, is the exact same thing as, these guys are the same thing. Nucleophilic acyl addition and reaction with a proton or other Lewis to form a resonance stabilized cation. I kind of count these as the exact same thing because this is nucleophilic addition in a basic environment, because we end up forming a negative charge, and this is nucleophilic addition in an acidic environment, because when we do the first step, we go, oh no, this is an acidic environment and we made a negative charge, we're not allowed to do that, and so we go back and change our first step. Which, by the way, on your exams, just so you know, it is entirely valid to as long as you're nice and clear about what you're doing, you can do this, go, oh no, that's not what I wanted, obviously. I know that this has to be in an acidic environment. And you can go like that, and hopefully you do your electron pushing with pencil so that you can get rid of this, and you can go, instead, I want blue for electron pushing. And then this guy attacks there and moves it. So if you draw this out, you can just very clearly scribble this guy out and do a nice little triangle thing there. Yeah, so you don't have to just erase everything. But it is a good idea to use pencils and have an eraser, four-side pencil, when you're doing electron pushing, at least for the mechanism questions. And I like to have mechanism questions. It's either 940 or it's like 947, because last time I looked it was 45, or 30, 35, whatever. Yeah, 38. So we're gonna stop here for today. If you have any questions, let me know. I put up your, yes.
So on Canvas, it says that the restitution worksheet was due at 10.
Yeah, I just sort of put them as like,
Okay, so we actually
yeah, no.
don't do it.
Everything on Canvas, I just put the due dates as the time at which it starts, because I figured it would be much less convenient to get a phone reminder that your exam is almost due while you're taking it, or like that your quiz is almost due while you're taking it. So, yeah.
So you teach our recitation?
I do not teach you recitation. You have 2 TAs, Nurul and Vandana.
Here.
It is,
It's in Swift.
it's not in here, it's in,
somewhere.
So, yeah.
Yeah.
We
the
have,
doors were always locked?
so she
Okay.
just, like, no
No
one
citizen
comes in
here.
here afterwards, we just stayed in here.
Okay,
I don't know if you have to ask someone about that, but it was
I
much
mean,
more efficient.
I
'Cause, like,
know.
we would literally be waiting
Yeah.
for like 15 minutes.
Yeah, that was
Oh,
so-
yeah, no, that's annoying and
Yeah,
we're
we
not
have
gonna
to
play
walk.
that game. Especially because to print out your exams, I usually have to call campus security
Yeah.
to get into the place with the copiers because they don't give me a key to that because I'm just a grad student. But I'm not just a grad student because I'm teaching. Campus
So-
security doesn't like that. Yeah, we can plan to have recitation in here. I will let my TAs know. Tomorrow.
Especially since we're also combining.
Yeah, fair enough. So we're combining and stuff. So we've got recitation in here unless someone comes in to kick you out, in which case we'll figure it out. There's no quiz tomorrow in recitation, and you will either have Nurul or Vandana. Vandana is spelled like Wanda, Wandana, just in case you're looking for emails. But their emails are also on the syllabus. I changed the syllabus last night, or yesterday at some point, to look like last year's syllabus, so you can like scroll through it and it's nice and pretty and formatted, rather than my mess of a Word document. And by tomorrow, I will know, I should know, otherwise I'm going to bother your TAs a bunch, when their office hours are, which means that I can set when my office hours are. Yeah. Their office hours are going to be in the TA area in Revachol, on Revachol 5th floor. My office hours, my office is, it's on your syllabus, but it's 825N, which is just, if you go to the 8th floor and you get off the elevator and you start looking around, there's these double doors, and they're not numbered, and it just sort of, they're always closed for some reason. And it looks like they enter into a room, but in fact, they just enter into the entire hallway. So, you're looking for those double doors, and then the first student office you get to on the right is gonna be me. Right across from that, on the left, there's a little nook with a round table and an entire wall of dry erase. So, I might also be out there, since I share an office. Yeah. All right, have a wonderful, not week,